Hi, myself I am Y Nitish Kumar from ITA section. My topic for max subject LAC is probability mass functions. Probability and statistics. A probability mass function is a function that gives the probability that a discrete random variable is exactly equal to some value. Sometimes it is also known as the discrete density function. The probability mass function is often the primary means of defining a discrete probability distribution, and such functions exist for either scalar or multivariate random variables whose domain is discrete. A probability mass function differs from a probability density function in that the latter is associated with continuous rather than discrete random variables. A PDF must be integrated over an interval to yield a probability. The value of the random variable having the largest probability mass is called the mode. Formal definition: probability mass function is the probability distribution of a discrete random variable and provides the possible values and their associated probabilities. The probabilities associated with all values must be non-negative and sum up to 1. Thinking of probability as mass helps to avoid mistakes, since the physical mass is conserved as is the total probability for all hypothetical outcomes. Measure theoretical formulation. A probability mass function of a discrete random variable can be seen as a special case of two more general measure theoretic constructions: the distribution of x and the probability density function of x with respect to the counting measure expected value. In probability theory, the expected value, also called expectation, expectancy, mathematical expectation, mean, average, is a generalization of the weighted average. Informally, the expected value is the arithmetic mean of a large number of independently selected outcomes of a random variable. The expected value of a random variable with a finite number of outcomes is a weighted average of all possible outcomes. In the case of a continuum of possible outcomes, the expectation is defined by integration. In the axiomatic foundation for probability provided by measure theory, the expectation is given by Lebesgue integration. History: the idea of the expected value originated in the middle of the 17th century from the study of the so-called problem of points, which seeks to divide the stakes in a fair way between two players who have to end their game before it is properly finished. This problem had been debated for centuries. Many conflicting proposals and solutions had been suggested for the years when it was passed to Blaise Pascal by French writer and amateur mathematician Chevalier de Méry in 1654. Méry claimed that this problem couldn't be solved and that it showed just how flawed mathematics was when it came to its application to the real world. Pascal, being a mathematician, it came to its application to the real world. Pascal, being a mathematician, was provoked and determined to solve the problem once and for all. He began to discuss the problem in the famous series of letters to Pierre de Fermat. Soon enough, they both independently came up with a solution. They solved the problem in different computational ways, but their results were identical because their computations were based on the same fundamental principle. The principle is that the value of a future gain should be directly proportional to the chance of getting it. This principle seemed to have come naturally to both of them. They were very pleased by the fact that they had found essentially the same solution, and this in turn made them absolutely convinced that they had solved the problem conclusively. However, they did not publish their findings, they only informed a small circle of mutual scientific friends in Paris about it. In Dutch mathematician Christian Huygens' book, he considered the problem of points and presented a solution based on the same principle as the solutions of Pascal and Fermat. Huygens published his treatise in 1657, De Ratio Sinis in Ludo de Alle on probability theory just after visiting Paris. The book extended the concept of expectation by adding rules for how to calculate expectations in more complicated situations than the original problem. and can be seen as the first successful attempt at laying down the foundations of the theory of probability. In the foreword to his treatise, Huygens wrote, "It should be said also that for some time some of the best mathematicians of France have occupied themselves with this kind of calculus, so that no one should attribute to me the honor of the first invention. This does not belong to me, but these savants, although they put each other to the test by proposing to each other many questions difficult to solve, have hidden their methods. I have had therefore to examine and go deeply for myself into this matter by beginning with the elements, and it is impossible for me for this reason to affirm that I have even started from the same principle. But finally I have found that my answers in many cases do not differ from theirs. Sample maximum and minimum. Statistics. The sample maximum and sample minimum, also called the largest observation and smallest observation, are the values of the greatest and least elements of a sample. They are basic summary statistics used in descriptive statistics such as the 5 number summary and Bowles's 7 figure summary and the associated box plot. The minimum and the maximum value are the first and the last order statistics. Probability mass function. In probability and statistics, a probability mass function is a function that gives the probability that a discrete random variable is exactly equal to some value. Sometimes it is also known as the discrete density function. The probability mass function is often the primary means of defining a discrete probability distribution, and such functions exist for either scalar or multivariate random variables whose domain is discrete. A probability mass function differs from a probability density function in that the latter is associated with continuous rather than discrete random variables. A PDF must be integrated over an interval to yield a probability finite. There are three major distributions associated: the Bernoulli distribution, the binomial distribution, and the geometric distribution. Binomial distribution models the number of successes when someone draws n times with replacement. Each draw or experiment is independent with two possible outcomes. The discrete distribution has two or more categories, one of which may occur whether or not these categories have a natural ordering. When there is only a single trial, this is a categorical distribution. An example of a multivariate discrete distribution and of its probability mass function is provided by the multinomial distribution. Here, the multiple random variables are the numbers of successes in each of the categories after a given number of trials, and each non-zero probability mass gives the probability of a certain combination of numbers of successes in the various categories. Multivariate case. Two or more discrete random variables have a joint probability mass function which gives the probability of each possible combination of realizations for the random variables. The probability mass function is also called a probability function or frequency function, which characterizes the distribution of a discrete random variable. Let x be a discrete random variable of a function, then the probability mass function of a random variable x is. And thank you. This is my presentation.